What exactly is a force? Really, like, what is a force? How would you define it? Now, most textbooks would say that a force is a push or pull action. And that's true. Let's say if you have a box, you can push the box with an applied force, or you can pull it with a rope, also known as a tension force. And so you could describe a force as a push or pull action. But now, what else can forces do? A force can cause an object at rest to enter a state of motion, like this box. It could be sitting at rest, and now it has a velocity. So if there's a net force acting on an object, there's going to be an acceleration, according to Newton's second law. Net force is equal to mass times acceleration. Now, if there's no net force, or if the net force is equal to zero, then it could mean that the object is either at rest or it's moving with constant velocity. Now, it's important to understand that there's many forces acting on an object. Even though you may have an applied force directed to the right, you can have a frictional force directed towards the left, opposing the motion of the object. It could be static friction if the box and the surface, if they're not sliding past each other, or if they are sliding past each other, it could be kinetic friction. You also have the weight force, which is basically the force of gravity that brings the block down, and also the normal force, which is exerted by the surface on the block. And so there's a lot of different forces acting on an object, and a diagram that shows all the forces acting on an object is known as a free body diagram. But what else can forces do? One important aspect of forces is that they can transfer energy. And let's think about that. So let's say if we have a block and a person applying a force to push the block. So what's really happening here? As the person pushes the block will begin to accelerate, which means that its velocity will change. So if the block is at rest, the velocity is now increasing, which means that the kinetic energy of the object is going up. Now, in order for the kinetic energy of the object to increase, that means that the person has to be expending energy to do so. And so it turns out that in order to increase the energy of an object, you have to decrease the energy of another object. And so energy is transferred here. And force is the mechanism by which two objects can transfer energy between each other. So let's say we have an ideal situation, and that the block gains 100 joules of energy. This would mean that the person has to lose 100 joules of energy. A good way to think about this is, let's say if you want to transfer $100 to your friend's bank account. In order for you to do so, you have to lose $100 in your bank account. Thus, in any transaction between a buyer and a seller, someone gains money and someone has to lose money. And the same is true in the case of a transfer of energy. One object will gain energy and the other object will lose energy. It's simply the way it works. The equation has to be balanced. So you could think of energy as a form of currency in the realm of physics. But now sometimes we may not have a perfect ideal situation. So let's say we have the same person, but let me draw him better. And let's say he's applying a force to accelerate this block. But this time, he expends 150 joules of energy. But let's say the block did not capture all of that energy. Let's say it captured only a portion of it. Let's say it captured 100 joules. The question is, where did the other 50 joules go? So 100 joules went to increase the kinetic energy of the block. The other 50 was lost in the form of heat or even friction. And so whenever you have an interaction between two objects, there's going to be some energy loss in the form of heat or friction. It always happens. And so these two are never equal unless you have a perfect ideal situation where no energy is lost due to friction. Now, another thing that forces can do is that they can change the momentum of an object. Now, what is momentum? Momentum is mass in motion. It's mass times velocity. So because velocity is a vector, momentum is a vector. It has both magnitude and direction. Now, based on Newton's second law, we know that the net force of an object is the product of its mass times acceleration. And acceleration is the rate at which velocity changes. It's the change in velocity divided by the change in time. And so if we were to replace acceleration with this expression, let's say if we were to substitute it here, we get this expression. The net force is equal to the mass times the change in velocity divided by the change in time. Now, if momentum is mass times velocity, then what is mass times the change in velocity? Mass times the change in velocity is the change in momentum. So this is another way in which you could define a force. The net force acting on an object is equal to the rate at which the momentum of that object changes. So if the momentum of an object changes rapidly, that means that you have a very strong net force acting on that object. If the momentum changes at a very slow rate, then there's a very weak force acting on that object. So here is a perfect example problem that will illustrate the effect of forces on an object's momentum and kinetic energy. So let's work out this problem. A 10-kilogram ball moving east at 12 meters per second strikes a 5-kilogram ball at rest. So let's begin with a picture. So let's say this is the 10-kilogram ball, and it's moving at a speed of 12 meters per second. And then we have another ball, a 5-kilogram ball, which is at rest. Now I'm going to put a line here. So on the left side, this is before the collision, and on the right side, that's going to be after the collision. So let's continue reading. After the collision, the 10-kilogram ball is moving east at a speed of 4 meters per second. And the 5-kilogram ball is moving east at a speed of 16 meters per second. So let's work on part A. Calculate the momentum of each object before and after the collision. We said that momentum is mass times velocity. So to calculate the momentum of the first object, it's going to be the mass of 10 kilograms times the velocity of 12 meters per second. So that's going to give us 120 kilograms times meters per second. Now I'm not going to write the whole unit here because if I do it for all four situations, I'm going to run out of space. Now for the second object, before the collision, the 5-kilogram ball, it's at rest, which means that its velocity is 0. And so using this formula, the momentum will also be 0. Now after the collision, the 10-kilogram ball has a speed of 4 meters per second. So 10 times 4 will give us a momentum of 40 kilograms times meters per second. Now the 5-kilogram ball has a velocity of 16 meters per second east. So 5 times 16 is 80. Now, here's a question for you. Is the total momentum conserved? What is the total momentum before the collision? Before the collision, it's 120 plus 0. And after the collision, it's 40 plus 80, which is 120. And so the total momentum is conserved in this situation. The momentum before the collision is equal to the total momentum after the collision. And for any collision, be it an inelastic collision or an elastic collision, the total momentum will always be conserved. Now let's shift our attention to something else. What is the change in the momentum of each object? So if we focus on the 10 kilogram ball, the momentum went from 120 to 40. So basically, the momentum decreased by negative 80. Now, if we focus on the 5 kilogram ball, the momentum went from 0 to 80. So it increased by 80 kilograms times meters per second. And so there's two forces in play here. The 10 kilogram ball exerts a force on the 5 kilogram ball, causing its momentum to go up from 0 to 80. At the same time, the 5 kilogram ball exerts a force on the 10 kilogram ball, decreasing its momentum from 120 to 40. And so whenever you have two objects colliding, there's two forces in play. There is the action force and there is an equal but opposite reaction force. And that's the basic idea behind Newton's third law. For every action force, there is an equal but opposite reaction force. And so when one object gains momentum, the other object will lose momentum. Now, let's shift our discussion from momentum to energy. So let's focus on part C. Calculate the kinetic energy of each object before and after the collision. So the formula that we're going to use to calculate the kinetic energy is 1/2 mv squared. So here, for the first object, we have a mass of 10 and a speed of 12. So it's going to be half times 10 times 12 squared. 12 squared is 144 times 10. Well, let's actually take half of 144 because that's 72, and then times 10. That will give us 720 joules. Now, the 5 kilogram object before the collision is at rest. So it has no kinetic energy because it's not moving. Now, after the collision, the 10 kilogram object has a speed of 4. And so 4 squared is 16. Half of 16 is 8. 8 times 10 is 80. So it has 80 joules of kinetic energy. For the last one, it's 1/2. That doesn't look like a 2. Let's fix that. Times the mass of 5 times the speed of 16, but squared. 16 times 16 is 256. And half of 256 is 128 times 5. I'm going to use a calculator for that. And so that's going to be 640 joules. So looking at part D, is the total kinetic energy conserved? And the answer is yes. Before the collision, the total kinetic energy is 720. After the collision, it's 80 plus 640, which is 720. So would you say this is an inelastic collision or an elastic collision? This has to be an elastic collision because kinetic energy was conserved. In an inelastic collision, kinetic energy is not conserved, but momentum is always conserved regardless of the type of collision you're dealing with. Now let's analyze the change in kinetic energy of each object. So for the 10 kilogram object, the kinetic energy went from 720 to 80. So we could say that it decreased by 640 joules of kinetic energy. For the other object, the 5 kilogram ball, the kinetic energy increased by 640 joules. So in this situation, this is an ideal situation where no energy is lost due to friction or heat. So all of the energy that was lost by the 10 kilogram ball was acquired by the 5 kilogram ball. Now let's move on to part E. Calculate the average force each object exerted on each other if the contact time is 0.1 seconds. So the formula that we're going to use is this. The force is going to be the mass times the change in velocity divided by the change in time. So focusing on the 10 kilogram ball, it has a mass of 10 and its velocity went from 12 to 4. So final minus initial, the final velocity is 4, the initial velocity is 12. And divided by the change in time, which is 0.1. So 4 minus 12 is negative 8 times 10, that's negative 80 divided by 0.1. So it's negative 800 newtons for the 10 kilogram ball. Now you might be wondering, why is that force negative? The reason being is that force is directed towards the negative x-axis. And it's going in the opposite direction of which the ball is moving. The 10 kilogram ball is moving to the right, and the force is directed to the left. So in this case, this force is acting in such a way to slow down the object. It's decelerating it from 12 to 4. That's why the force is negative. Now let's calculate the force acting on the other object using the same equation. So the second ball has a mass of 5 kilograms and its speed increases from 0 to 16. So the final velocity is 16, the initial velocity is 0, and the contact time, the time where the two objects are touching each other, it's 0.1 seconds. So we have 5 times 16, which is 80, divided by 0.1. So that's 800, but this is positive 800. So notice that these two forces, they're equal in magnitude, but they are opposite in direction. So let's summarize what we've learned about forces in this video. So here is the 10 kilogram ball, and here is the 5 kilogram ball. So in this collision, we saw that the 10 kilogram ball exerted a force of positive 800 newtons. And the reason why the force is positive is because it caused the object to speed up from a speed of 0 meters per second to a speed of 16 meters per second. And so a force can cause an object to accelerate or increase its velocity. Now, even though the 10 kilogram object exerted a force on a 5 kilogram object, the 5 kilogram object also exerted an equal but opposite force of negative 800 newtons on the 10 kilogram object. So Newton's third law is being observed here. For every action, there's an equal but opposite reaction force. I meant to say for every action force, there's an equal and opposite reaction force. So when the 5 kilogram ball exerted an equal but opposite force of 800 newtons, it caused the 10 kilogram ball to decelerate from a speed of 12 meters per second to a speed of 4 meters per second. In this process, the 5 kilogram object gained a momentum of, what did we say it was? 80 kilograms times meters per second. And the 10 kilogram ball, it lost a momentum of 80 kilograms times meters per second. At the same time, the 5 kilogram ball gained 640 joules of kinetic energy, while the 10 kilogram ball lost 640 joules of kinetic energy. And so this really helps us to see how forces act on two interacting objects. So these forces, they're equal but opposite in magnitude, and they can cause the kinetic energy of one object to increase by decreasing the kinetic energy of the other object. And at the same time, they can increase the momentum of one object, causing a corresponding decrease in the momentum of another object. So force is the mechanism by which one object can transfer energy or momentum to another object, and vice versa. So that's the way I think of forces. Nevertheless, you can still think of forces as a push or pull action, because the 10-kilogram ball does push on the 5-kilogram ball, and likewise the 5-kilogram ball pushes on the 10-kilogram ball. And don't forget about these equations. Anytime there is an acceleration, there is a net force acting on an object. And you can also define a net force as being the rate at which the momentum changes. That's a terrible looking T. So you can calculate the average net force by using this formula. Mass times the change in velocity divided by the change in time. And so there's many different ways in which you can calculate forces or describe them. So that's all I got for this video. Feel free to subscribe if you like it. And don't forget to check out my new physics video playlist that I have on my channel. So feel free to take a look at that. I also have other videos on math, chemistry, and other stuff. You'll find it when you take a look at it. Thanks for watching.